In this video, we will be solving question number 56 from GATE 2023 Biotechnology paper that carries 2 marks. The question is, if 1000 base pairs of a double helical DNA weighs 1 into 10 power minus 18 grams and distance between two base pairs is 0.34 nanometers, the total amount of DNA in milligrams rounded off to one decimal place required to stretch from Earth to Moon, assuming the distance between the Earth and the Moon is 3,74,000 km is. So here we are required to calculate the amount of DNA in milligrams required to stretch from the Earth to the Moon. So before we go ahead with solving this problem, let's just look at some interesting facts. We all know that the diploid human genome has 23 pairs of chromosomes. So the DNA in each cell is packaged into 46 chromosomes in the nucleus. So as well as being a naturally helical molecule, the DNA is supercoiled using enzymes and chromatins that holds the DNA together, that coils the structure so that it takes up less space. Like, let's say, for example, try holding a piece of string at one end and twisting the other. So as you keep twisting, the string creates coils and coils and eventually so many coils. So your DNA is arranged in a similar manner as a coil of coils of so many coils. So this allows the huge 3 billion bases of the human genome in each cell to fit into a space as small as just 6 microns. So if you stretch the DNA in one cell all the way out, it would be about 2 meters long, and all the DNA in your cells put together would be about twice the diameter of the solar system. So that's how big the DNA is, although it's very small, we can't even look with our eyes. So moving on with to our question. So here is the solution to the problem, but to have a better understanding, let's solve it step by step now. So let's first state out the values that are given in the question. So we have weight of 1000 base pairs of DNA is equal to 1 into 10 power minus 18 grams. We also have the distance between two base pairs. So let's consider that to be small d. So distance between two base pairs, small d, is equal to 0.34 nanometers. So we all know that 1 nanometer is equal to 10 power minus 9 meters. So let's just stick to the standard unit, which is meters. So converting this value, we have small d is equal to 0.34 into 10 power minus 9 meters. And next what we have is the distance from Earth to Moon. So we have the Earth and we have the Moon. So the distance between the Earth and the Moon is 3,74,000 kilometers. So which is equal to 374 into 10 power 3 kilometers. And again, converting this to meters, we have 374 into 10 power 6 meters, because 1 kilometer is 1000 meters, which is equal to 10 power 3 meters. And because we already have a 10 power 3 here, adding it up, we get 10 power 6 meters. So let's consider this to be capital D. And next we now have to calculate how many bases of DNA are needed to stretch all the way to the moon. So let's calculate the number of base pairs. So number of base pairs is equal to the distance from the earth to the moon divided by the distance between two base pairs. So we have both of these values now. So just writing it down, capital D is 374 into 10 power 6 meters divided by small d is 0.34 into 10 power minus 9 meters. So let's first keep the numerator as such for now. 374 into 10 power 6 divided by, let's just shift the decimal places here. So let's make it 34 into 10 power minus 2 into 10 power minus 9. So adding it up, we get 10 power minus 11. And then now moving this up to the numerator. And before that, let's cancel this out. So this would be 11. 374 divided by 34 would be 11. So now we would have 11 into 10 power 6 into, moving this to the numerator, we have 10 power 11. Now adding these up, we have 11 into 10 power, so 6 plus 11 is 17. So we have 11 into 10 power 17 bases. So this means that we would need 11 into 10 power 17 bases of DNA to stretch from the earth to the moon. So now that we have the number of bases needed, we need to calculate how much it weighs. So because that's what was asked in the question, the weight of DNA, the amount of DNA in milligrams needed to stretch from the earth to the moon. So now let's calculate the total amount of DNA. So weight of DNA in grams, because in question we have the given weight is in grams. So let's first use that in our calculations. So the weight of DNA would be number of base pairs into the weight of thousand base pairs of DNA. So we just calculated that the number of base pairs needed to stretch from the earth to the moon is 11 into 10 power 17 base pairs multiplied by the weight of 1000 bases is 1 into 10 power minus 18 grams. So this, because this is for 1000 bases, we divide it by 1000, because we need to multiply the weight of the total number of bases into the weight of a single base. So because the given weight is for 1000 bases, we divide the value by 1000. So now again, moving one decimal place here, we would have 11 into 10 power 17 would become 1.1 into 10 power 18 into the 10 power minus 18 we have over here, and divided by 1000. This unit is still in grams. So now these two would get cancelled out. So now we have 1.1 into 10 power minus 3 grams. But the question was, like, we have to answer the question milligrams. So this would become 1.1 milligrams, because 1 milligram is equal to 10 power minus 3 grams. So yeah, the final answer to your question is 1.1 milligrams. Thank you.